Welcome everyone. I'm excited to kick off today's presentation on key equations, concepts, and practical examples. This is the cover slide, so I just want to briefly introduce what we'll be exploring. We'll go over some fundamental equations, important concepts, and real-world applications that will help deepen your understanding. So let's get started and dive into the fascinating world of these key topics. Let's take a look at the first law of thermodynamics, which is fundamental to understanding energy changes in a system. The key equation here is ΔU equals Q minus W. This means that the change in the internal energy of a system is equal to the heat added to the system minus the work done by the system. Essentially, if you add heat, you're increasing the system's energy, but if the system does work, it uses up some of that energy. For example, suppose we add 500 kilojoules of heat to a system. If, during that process, the system does 200 kilojoules of work, the net change in internal energy, ΔU, would be 300 kilojoules. This example highlights how heat and work directly influence the energy content of a system, which is a crucial concept in thermodynamics. Connecting this to the overall theme, understanding this relationship helps us analyze real-world energy systems, whether in engines, refrigerators, or power plants. It's all about tracking how energy flows and transforms within systems. Let's take a closer look at enthalpy and internal energy. Enthalpy, denoted as H, is defined as the internal energy U plus the pressure volume work, which is PV. So H equals U plus PV. When we talk about changes, the change in enthalpy, delta, equals the change in internal energy, ΔU, plus the work done by pressure volume expansion, which is P times delta. To make this clearer, consider an example. Imagine steam expanding from a volume of 2 liters to 3 liters at a pressure of 100 kilopascals. The change in enthalpy, delta in this case, would be 100 kilopascals multiplied by the change in volume, which is 1 liter or 1 cubic decimeter. So that's 100 times 1, resulting in 100 kilojoules. This example highlights how we can quantify energy changes during processes like expansion. Understanding these relationships helps us analyze energy transfer in thermodynamic systems, which is fundamental to our overall discussion of energy efficiency and system performance. Let's take a closer look at the ideal gas law, which is PV equals nRT. This equation is fundamental in understanding how gases behave. It relates pressure, volume, and temperature to the amount of gas, measured in moles. For example, if we consider 1 mole of air at a temperature of 300 Kelvin and a pressure of 101 kilopascals, we can calculate the volume using the formula. Plugging in the numbers, we get V equals 8.314 times 300 divided by 101, which is approximately 24.7 liters. This example highlights how the ideal gas law allows us to predict the volume of a gas under specific conditions, connecting pressure, temperature, and amount of gas. It's a powerful tool that helps us understand and manipulate gases in various scientific and engineering applications. Now let's take a closer look at the second law of thermodynamics. As you can see, it's expressed with the equation equals delta Q rev divided by T, and the key inequality that the total entropy change of the universe, delta SUNIV, is always greater than or equal to 0. This tells us that in any real process, the total entropy either increases or remains constant, but never decreases. For example, imagine heat flowing from a hot object at 500 Kelvin to a cooler one at 300 Kelvin. If 10 kilojoules of heat transfer occurs in this process, we can calculate the total entropy change as 10 times the difference between the reciprocals of the temperatures. When we do the math, it comes out to approximately 0.0133 kilojoules per Kelvin, which is positive. This positive value confirms the second law. Processes tend toward increasing entropy, and spontaneous processes are irreversible in nature. Connecting this to our overall theme, the second law helps us understand the fundamental directionality of natural processes, which is crucial in designing efficient energy systems and understanding the limits of energy conversion. Let's take a closer look at Fourier's law of conduction. Essentially, this law explains how heat flows through a material. The formula is Q equals negative K times the temperature gradient dt/dx. Now, Q here represents the heat flux, or how much heat is passing through a unit area per second. The negative sign indicates that heat flows from high to low temperature, opposite the temperature gradient. The thermal conductivity, K, is a material property showing how well the material conducts heat. For example, if we consider a wall with a thermal conductivity of 1.2 watts per meter Kelvin, and there's a temperature difference of 20 degrees Celsius across a thickness of 0.05 meters, we can calculate the heat flux. Plugging in these values, the heat flux Q comes out to about 480 watts per square meter. This calculation helps us understand how much heat passes through the wall under these conditions. Understanding Fourier's law is crucial because it provides a quantitative way to analyze and predict heat transfer in materials, which ties directly into the overall theme of thermal management and insulation strategies we're exploring. Let's talk about convection heat transfer now. The fundamental equation we use is Q equals H times A times the difference between the surface temperature, Ts, and the surrounding temperature, T infinity. Essentially, this tells us how much heat is being transferred through convection based on these variables. For example, imagine a plate at 80 degrees Celsius sitting in 25 degrees Celsius air. If the convective heat transfer coefficient, H, is 25 watts per square meter Kelvin, and the plate has an area of 1 square meter, then the heat transfer rate, Q, comes out to about 1375 watts. This example helps us see how the different factors, temperature difference, surface area, and the convective coefficient, combine to determine the heat transfer rate. Understanding this is key because convection is a dominant mode of heat transfer in many practical situations, from cooling electronic devices to designing HVAC systems. So, grasping how to apply this equation allows us to predict and control heat transfer more effectively, which ties back to our overall goal of optimizing thermal management in engineering systems. Now, let's delve into thermal radiation. The key equation here is Q equals sigma times epsilon times A times the difference between the fourth powers of the surface temperature, Ts, and the surrounding temperature, Tsur. This might look a bit complex at first, but it captures an essential concept: how objects emit and absorb radiation depending on their temperature. For example, imagine a black plate at 600 Kelvin. If the surrounding temperature is 300 Kelvin, we can estimate the heat transfer rate, Q, using this formula. Plugging in the numbers, we get approximately 6.12 kilowatts per square meter. This example highlights how significantly thermal radiation depends on temperature raised to the fourth power, which is why even small temperature differences can lead to large heat transfer values. Understanding this helps us grasp how objects exchange heat in many real-world scenarios, tying into the overall theme of heat transfer mechanisms. Now let's look at the heat exchanger using the LMTD method. The heat transfer rate, Q, is calculated with the formula Q equals U times A times ΔTlm. Here, U is the overall heat transfer coefficient, O is the heat exchanger area, and ΔTlm is the log mean temperature difference. The key point is how we determine ΔTlm. It's given by the difference between the temperature differences at the two ends, ΔT1 and ΔT2, divided by the natural logarithm of their ratio. So ΔTlm equals ΔT1 minus ΔT2 divided by ln, ΔT1 over ΔT2. Let's consider an example with a counterflow heat exchanger. Suppose the inlet temperatures are T1 at 100 degrees C and 30 degrees C, and the outlet temperatures are 60 degrees C and 70 degrees C, respectively. That gives us ΔT1 as 100 minus 60, which is 40 degrees C, and ΔT2 as 70 minus 30, which is also 40 degrees C. Since both temperature differences are equal, the ΔTlm simplifies to just 30 degrees C in this case. This example highlights that in a counterflow exchanger, when the temperature differences at both ends are equal, the calculation becomes straightforward. Overall, understanding how to accurately determine ΔTlm is crucial because it directly impacts the heat transfer rate calculation. This method helps us evaluate and optimize heat exchanger performance effectively. Let's take a moment to look at this final slide, the summary chart. Here, we've compiled all the formulas we've discussed, complete with their units and quick examples side by side for easy reference. This chart is really designed to serve as your quick go-to guide, helping you recall key calculations efficiently. The most important thing to remember is that understanding these formulas, along with their units, is crucial for accurate and consistent results in your work. When you see a formula, check the units to ensure you're applying it correctly. This helps prevent common errors. Connecting this to our overall theme, mastering these formulas, and being able to reference them quickly reinforces the importance of precision and clarity in our calculations. It's about building confidence so you can focus more on analyzing and applying data, rather than constantly looking up formulas. So keep this chart handy, review it regularly, and use it as a quick reference whenever you're working through your projects. It's a simple but powerful tool to help solidify your understanding and streamline your workflow.